Hey guys, real quick announcement. I'm going to be out in LA next week, and we're going to try and do a meetup out there. So if you're in the LA area and you want to come and drink some beers and hang out and talk about electronics, it's also possible some of the Hackaday folks might be there. So keep your eyes and ears open for an announcement on the Amp Hour this week on theamphour.com, and I'll try and send that out via Twitter and everywhere else. But hopefully we'll be able to get together for a hangout in person, and we can all meet one another. All right, on with the show. This is the Amp Hour Podcast, recorded February 17th, 2014, episode 185, with guest Hank Zumbahlen, Zoppa, Zumbahlen, Zateticism. Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
And I'm Michael Osman of Gray Scott Gadgets.
And I'm Hank Zumbahlen from Analog Devices.
Welcome, Hank.
Thank you.
We have a non-standard co-host here today. Mike joined us again because Dave couldn't make it, but we're glad to have him. And we're gonna throw as many analog questions as we can at Hank because I think he's probably the most analog guru we've had on the show to date, and I'm super excited.
Thank you, Chris, for having me because I'm excited to get to talk to Hank.
Yeah. The only downside, I think, to doing a show audio-wise is that I feel like Hank could draw us enough like PCB layout diagrams to kind of take us through the rest of the day and tomorrow as well. And so we won't have that, but hopefully we can do it by audio.
Oh, by the way, when I said I was going to be here all night, I wasn't really serious about all night.
Okay, not all night. Okay. All right, fine. So, hey, Hank, could you give us a little bit of your background, how you've come up through engineering through the times, and then kind of bring it to the current day and your writings that we all benefit from?
Okay. When I graduated from college, I went to the University of Illinois. I graduated in 1974. And I got a job immediately out of college at National Semiconductor. Nice. They worked me for about 2 months, and again, then I got laid off.
Oh, jeez.
They spent more on getting me out to California than they did in my paycheck for the time I worked for them. So after that, I got into the system design part of it. I worked at a company that made telecom test equipment, Halcyon, no longer among the living.
Rest in peace, Halcyon.
Then I went to a test equipment manufacturer for integrated circuits. They're still in business, but just not the group that I worked for. I have that magic touch with you hire me, you better start looking for other employment. I haven't been able to kill analog yet.
Oh, great.
I've been there for a while. But after I worked at Sentry Test Systems, and I was at Signetics for a couple of years, and then I went to Analog Devices, and I've been there almost 25 years now.
Wow, that's awesome. So I mean, that's a lot of test equipment stuff there. Obviously, you've been on your rampage throughout the industry, taking companies down with you as you go. So when you say system, though, what do you mean by system level engineering? Do you mean like board level versus silicon, or how do you define that?
Yeah, I mean board level and integrating it into a whole system. Okay. Not integrated circuit design, but taking ICs and stuff and making systems out of them.
Well, that's good, yeah, because I mean that's the kind of stuff I think a lot of our audience does. I mean that's what I do. I think Mike, that's what you do. Mike writes
Definitely.
A lot of software too. He's an outsider.
Yeah, I never got too good at diddling bits. So
at Analog Devices, then, so that means that you were more on the application side of things and kind of and developing the system level applications.
Yeah, I've been an application engineer the entire time. I started as a field applications engineer and then worked into the central applications group. I spent several years doing seminars and the like, which the that job kind of went away because we stopped doing the seminars as often as we were doing them before. And during the whole time, I've been involved in trainings and doing the writings and things like that on as kind of a sideline to the job.
Yeah, so your book, Linear Circuit Design Handbook, I was looking around online a little bit, and so there's I guess it's an older version of it that is available in PDF form from Analog Devices, but the newer version is in print. Is that correct?
They're pretty much the same. There's slight differences between it. The one that's available PDF, there was a chapter in there that had a lot to do with tools available from Analog, and we basically left that out of the print version. Other than that, they are pretty much the same, and they're both of roughly the same genealogy. I think we published the Analog Devices version about 2005, and then the Elsevier did one. They basically took the book and then relayed it out to their format, and so it was like a year and a half after that it came out.
So is that book basically an outgrowth from your training and seminars?
Yeah, we like to call it the seminar that never was.
Like
at the time, we were doing seminars like we did in 2002. We did one on op amps that was basically Walt Young. It was his last version of his op amp cookbook type of thing. The next year, we did one for converters, both of which were then converted into the books as well. And then this one was done as kind of a lump together of those two topics plus other stuff has to do with sensors and the like. And it never really got to the point of actually going on the road as a seminar.
I have to say, so when I first found, I forget what I was Googling around for something, and one of the chapters came up, and I think it might have been about the data converter stuff that's in there. And I remember I found the PDF and I started reading through it. I'm like, wow, this is just a great chapter. I can't believe they left it online. And then I kind of like started, playing with the URL there, and I'm like, oh my god, they left all of these PDFs out here. And I'm kind of like looking around, like I wonder if they're gonna catch me. And then I realized that then of course, like a month later, someone sent me the page that lists all the PDFs and that they're all yes indeed free. And I'm like, oh man, I thought I beat the system.
Yeah, it's a really good resource.
Oh man,
yeah, I still use it. My job today has a lot to do with answering technical inquiries and things like that. So I still use it, and I still send out links to it all the time because it is a pretty good general composite of most of the stuff you need to know.
Yeah. Oh, yeah. I mean, I've been pointing at, and so I have this new course, Contextual Electronics, and basically I've been pointing everybody at it too, just like, oh, I have a question about grounding, I have a question about linear regulators, that kind of stuff. It's like, nope, go check out this handbook. It's definitely, and I think the thing that's interesting about that too is that a lot of bigger companies might not realize that, having this kind of stuff free and out there online, it builds this goodwill towards the company as well. It's like, I think, oh, Analog Devices, yeah, they got this great book online. I mean, I don't know if I'm allowed to say as much, but I think the same kind of thing about Linear Tech and LT Spice, just like having free resources endears me to the companies that give me said free resources, including access to people like yourself. I mean, that's just a really valuable thing. Well,
and in point of fact, integrated circuits are kind of stupid by themselves, and if you don't know how to hook them up together, they don't do a whole lot. So, it's part of being able to get things to work. And, applying integrated analog, specifically integrated circuits, there's some things you need to keep in mind while you're trying to do that to get it to work right.
When you mentioned, so we were talking before the show as well, that a lot of the content in that book and your app notes and your content comes from your own frustrations and wanting to basically help people reduce their banging their own heads into the wall at 2 a.m, that kind of thing.
Yeah, I mean, pretty much that's it. If you want to think of it as a kind of a, I've been there, and I'm gonna try to help you not make the mistakes that I made before, because we find that people tend to do the same things as everybody else does because it's the most logical thing, and the kind of mistakes that people make are typically repeated, and specifically in the area of grounding and power supply decoupling and the like. That's something a lot of people take for granted until it turns around and kind of nips them in the hind end,
Yes. At 2 a.m, of course.
Yeah.
The day before it's due. Yeah.
Well, I've had my share of having things not go exactly the way you expect to, and you're up against a deadline. You have to get something out at a certain time, and things just aren't cooperating with you. And it's main thing in my life now is to try to reduce stress as much as possible.
That's good. Very zen. Very zen.
So, what's it like working for Analog Devices, and what location are you in?
I work out of the San Jose office, although a lot of the time I actually work out of a home office, but I'm associated with San Jose. I did a lot more, when I was actually working as a field applications engineer, because then I was interfacing a lot more with our sales guys, going out to customer sites and the like. Now most of the interfacing I do with customers is phone support and email support. I do get mailed out pretty regularly to do training for our distributors, because most of the distributors have now put in applications people, and we need to keep them as up to date as we possibly can. And that's one of my major job functions of late.
Do you ever do any public seminars where people can kind of hunt you down and find you and ask you questions in person like that?
Yeah, it happens. Not as much as it used to. I mean, like I said before, that about 10 years ago, that was the main part of my job, doing the seminars. Now it happens less frequently. Yeah. But Analog just went through a series of seminars, started last June. We called it Design Conference 13. Actually, I guess it started in May. And we did them in a couple of cities, and then we did an online version. And I went out and did the U.S. versions. I got mailed over and did a couple over in Germany. So it does happen. I enjoy doing that, so I kind of wish it happened a little bit more.
Yeah, it's nice to probably get out and meet people and see the ones who are actually having problems versus, I think that's kind of the problem with a lot of, I mean, I even feel this on the other side, trying to, talk to people who want to help me out, like FAEs or factory applications engineers. And it's like the default response is always, well, send me everything you can by email and I'll try and piece it together. Whereas before, I'm sure you were able to be like, okay, can we go back in your lab and you can just point at the thing? I'm sure that's challenging these days.
Yeah, not doing the field job anymore, so I don't know how quite that's going. But when I was doing that a lot of time we would go back into the lab and sit there and kind of poke around on a board. And, after having spent some years trying to debug circuits, you develop a few little techniques to go in and look at things that other people may not know, and I think that it's kind of a nice feeling from my point of view to be able to go in there and to help people out. It gives you a nice feeling.
Yeah, you're like Superman at that point. You like swoop in.
I don't know if I go that far. But
allow me to place the finger of wisdom onto your circuit and impart the capacitance of awesomeness.
Oh no, seriously, there was one time where I did something very similar to prove somebody that he had a bit of a problem. I actually stuck my finger in and changed the whole parameter of what was going on. Is because he had a grounding issue. And adding a little bit of stray capacitance and the antenna effect of my body. Once he saw that, he started to understand what the kind of things he had to do to kind of improve his circuit. And it's not all the stuff that appears on a schematic.
Yeah,
How you lay things out can have a pronounced effect on how a circuit works.
Speaking of grounding, your article, "Staying Well Grounded," is a terrific article. It's one that Chris pointed out, and it's one that I had kind of forgotten about, but I had seen that months or years ago, and it was it demystified a lot of things for me, especially dealing with data converters, and like the insights in that article about the analog ground versus digital ground on the same chip and what to do with them. I found that very helpful personally.
Yeah, me too. Between that article and then I think Henry, former guest Henry Ott as well, had another analog to digital converter article as well. I think those two basically carried me through my past two jobs completely. Yes, boss, I do know what I'm talking about.
Yeah, it's one of the things we continually run into. And that's why we spend a lot of time talking about it. And we found that when we were doing the seminars, the practical stuff we always would keep in the last quarter of the seminar, because it's usually day-long things divided up into 4 sections. The last section usually was the practical stuff, had to do with grounding and power supplies and stuff like that. Again, things that people don't really think about until it causes them all sorts of grief.
What would you say? So you run into this kind of decoupling stuff and grounding issues. What are some of the more common issues that you see aside from those? Are those kind of really the biggest ones, or do you see other stuff that pops up a lot?
I would say that they're two of the major things, but not by any stretch of the imagination the only. There's a lot of other things, but that common theme of decoupling and especially trying to explain the rationale behind decoupling. Do I really have to put these capacitors right at the chip? Yeah, pretty much.
Only as close as possible and no closer.
Right. When I was back in school, I learned that capacitances in parallel add up. So I've got a 10 microfarad here. What is this 0.01 going to help? The thing is that the analogy that I like to use a lot is hi-fi speakers. You have woofers and you have tweeters. Woofers handle the low frequencies, the tweeters handle the high.
Yep.
And neither one does a very good job of doing what the other one's supposed to, and that's the way it is with capacitors. You have the reservoir of charge, which would be the electrolytics 1000 mic, whatever it is, which is a local reservoir of charge, and then you have the higher frequency, which are basically designed to keep the noise out of the chip to start with, and they are both optimized for doing what they're supposed to do.
Yeah.
The capacitors are never strictly capacitors. They're a complex system. It's inductors and resistors and capacitors, and trying to understand that and keep that in your head is one of the true tricks of the trade.
So is it for you? Is it mostly just experience and kind of seeing these patterns over and over again, or how, do you have any rules of thumb that you follow or anything like that?
Well, a lot of it has to do with experience. A lot of it has to do with talking with other people and seeing what kind of issues they have. Because like I said before, there's a lot of times that the basic problems, the simple things, tend to be repeated by people all the time. And so you keep seeing the same thing. So that says, well, obviously this is something people need to be kind of warned about. And none of us live in a vacuum. So me talking to other people and other people talking back at me about different things, you get, even though you haven't had the experience yourself, you can learn from what other people have done as well.
So how about a quick rundown of this? Because this, like Mike said, this Staying Well Grounded article, one of my favorites personally. What about the whole why why can't I hook the D ground and the VDD digital to the digital power supply and the digital ground? Could you give us a quick rundown on that? Because I feel like that is like that was a big turning point.
Yeah, that's a big issue. Let me start out by saying that I wish I could find the guy who had the idea of making your power supply return and your reference node the same thing.
Yeah.
I wish I could find him and turn him into a speed bump.
We can do that. We can we have a wide network here. I'm just saying,
it's one of the worst ideas we've ever had. But that ship's already sailed. So now we have to do is figure out how we can make the most out of what we got. The issue has to do with, when we are drawing our schematics, we put whatever your favorite ground symbol is, triangle or little rake looking thing or whatever. And we assume that they're all at the same potential. And it's not the case.
Right.
Especially as you get up in higher frequencies, because there's not only a small amount of resistance, but a small amount of inductance, which obviously changes its impedance with frequencies. So when we draw these triangles on our schematic, we're assuming they're going to be the same, but it's really not going to be. And so the whole idea is that digital, especially if it's CMOS, which is one of the more common structures we use nowadays, the way CMOS works, it actually shorts the power supply for a very short period of time as it's transitioning from low to high. And so that causes a lot of current spikes. Not only that, with the clock speeds getting where they are today. I mean, when I did my first microprocessor-based system, we had this screamingly fast 1 megahertz master clock.
You can do a lot with a meg. You can do a lot.
Well, we did. I mean, but the issue is that that is just the fundamental frequency.
Right.
If you take a look at the harmonics, they go all the way up from there.
Yep. Stupid sharp corners all over the place.
Yeah. Fast rise times. And so all those current spikes have to go someplace, and it's a loop. They all, circuits are always loops. Even if we only draw one wire on our schematic, there's always a return, because wherever things are going, they have to come back. And so kind of keeping that's kind of the whole philosophy. And that's why you operate the digital ground separately from the analog ground, because the digital ground is going to have a lot of these return currents that you don't want flowing through the sensitive analog. One of my favorite examples, I think is in that article that you guys keep mentioning, is that there's a instrumentation amplifier that's really low power. And the quiescent current of that amplifier going through a 5-inch trace, I think I'd have to go back and look, but a relatively short trace, will generate an offset higher than the offset of the part itself. So those are the kinds of things that really sneak up on you, because, it's like microamps. And even if your ground is milliohms, the offset of that part's only like 7 microvolts to start with. So, it's something that unless you get hit in the head with it, you may not think about. And that also, things like capacitively coupled noise in an IC itself, depending on the size of the package, you're going to have bond wire coupling parasitic capacitances of, something on the order of some fraction of a picofarad, which again doesn't seem like much. But when you start putting these high frequencies in through these wires, that they will talk across into the sensitive analog inputs, and that's a big problem as well. So trying to keep, the analogy I use a lot is think like an electron. Try to see where you're going to flow, and remember that that it's always the path of least impedance. That's the way everybody works, So if I get a low impedance path through the analog ground, that's where I'm going to go. And if you don't want me to do that, then you have to kind of shovel me over someplace else. That's really the trick.
Do you ever find yourself worried about quantum effects when you're thinking like an electron? Oh, I know where I am, but I don't know how fast I'm going.
I never get to that kind of detail on it.
I know.
But it's the idea is just basically you got to kind of visualize where the currents are going to flow, and you keep the heavy flow out of the sensitive areas. That's the first thing you need to do when you're setting up your system, which is why when you're laying out a PC board, almost as important as the total schematic to start with is how you partition that out and keep things so that you don't have these chances of these high current, high noise, high frequency things getting into your high sensitivity analog areas. So how you lay out your board can have a pronounced effect on how things are done as well.
So I'm intrigued by your idea of separating the reference from the return. Is that a concept that can be used practically today, or I mean, have you seen designs that do that have like a separate reference plane that's completely different from the return power supply return, or is it a case where we would need a fundamental change to the way our ICs are made to really take advantage of that type of approach?
Well, it's not so much in the ICs, because once you get inside the IC, you don't really have a lot you can do about how the grounds are separated anyway. It is a concept that has been used. I mean, I still play around in the audio domain. I still play around with designing stuff myself for my own use, and that's always how I do it. I've talked to other people about it, and some other people have adopted it. It's you got to remember that there's some other things that you got to worry about. For instance, if you have multiple ground planes, where do they connect? They all have to go together someplace.
Mm-hmm. Yeah. And how does your CAD program do it too? Because that's always a stinker as well.
I mean, that's one of the big problems with CAD, and back in the good old days when we used to lay them out by hand.
Yeah, you just draw the connection, right? It just overlaps, and you're like, oh, it's done. It's right there.
Yeah. Another interesting story. When I worked at Century, I was developing a system that was for testing power regulators. Like a National at that time had announced a 20 amp linear regulator, and there was nothing on the market that would test it. So we tried to come up with something, and our first design, we were going to use a switch mode power amplifier, because the way it was defined, it had to be plus or minus 64 volts at plus or minus 24 amps, 4 quadrants square quartered.
Whoa!
Oh my goodness!
So you don't get to take off the corners like you usually do because of extra power, right?
Nope. So if you take a look at the worst case, it's been a long time since I did this, but if I remember the numbers right, it was like 3,500 watts possible dissipation in this thing if you got going in one of the odd quadrants where you have like minus voltage and minus current. So.
Wow.
What'd you use for a heat sink, like a Boeing 747 or something?
That was, well, actually it's one of the reasons why we went to a switch mode to start with, to try to keep some of that down. As it turned out, we couldn't quite get the switch mode stuff to work.
You're forgiven.
It worked.
It's okay.
It worked, but what the problem was it was also defined to be a 16-bit system, and we had a very hard time maintaining the linearity down to a 16-bit level, as you might guess.
Yeah.
Wow.
Yeah.
Especially when was this? Like the early 80s or something?
Yeah.
Wow.
Wow. Yeah. 16-bit wasn't as common as it is these days,
right.
anyways.
No, I mean the ADD converters were hybrids. It was.
Wow. And what this was to test. You said this is to actually test out a new chip. Is that right?
Yeah, it was National had announced a 20 amp linear regulator, part of their 7800 series types things, and so it was kind of aimed at that kind of thing. Also thinking that, well, if one guy does it, then some other people are going to want to do it too. So, there should be a market out there for it.
Yeah, I mean, people need to heat their homes, right? I mean, they.
Oh yeah. It turns out that we ended up having to scrap the switch mode and go to a standard linear amplifier that had basically the same specs, and so the power supply on that thing was amazing. I mean, it was just it was like the coupling capacitors. It had 65 volt rails, and the coupling capacitors was something on the order of about 3 farads.
So we took these trash cans, we filled them up with coils of paper and liquid.
Yeah, it wasn't quite that, but it was pretty close.
Yeah. Wow.
Actually, my technician, I told him, whenever you're going to start messing with this thing, turn it off, go get some coffee, come back in about 20 minutes. Yeah. Because I put bleed resistors on it, but, for practical reasons, the time constant was still pretty long. Yeah. Well, he didn't listen to me.
Oh, no.
And so he let it set for about 5 minutes, and he decided he was going to short out whatever charge was left with a screwdriver.
Does he still have all his fingers?
He has his fingers, but he doesn't have a screwdriver.
The thing vaporized, right?
It did.
Photonic induction would like to talk to him.
Wow. So, that was one of the more humorous things. I bet it made a hell of a noise too when he popped that.
Yeah. Wow. What kind of package does that come in? Like a something that's
it was a TO3.
TO3. Okay, one of those big metal.
As I remember, yeah.
Yeah. Buckets of heat thermal paste and.
Well, see, that's why it never really took off, and I don't think it actually stayed on the market very long, because the whole practical issue of trying to dissipate any kind of voltage drop between the input and the output, if that's got any kind of value to it at all, times the 20 amp possibility of going through there, you start getting into a lot of watts pretty quick. And just the practical concern of trying to heat sink that was non-trivial.
Right. And you always get the edge on that number, right? 125C, that's all you get. You just got to stay away from that number before your silicon starts to go bad.
That's right.
That's crazy. Oh, man.
I forgot where we were going with that.
Yeah, anyway. I do too. But who cares? That's such a great story. So I was going to ask, because Mike's here and he's doing RF stuff, how much of your stuff is touching on RF these days, if not in a direct manner of actually generating or measuring RF, but also just dealing with the increased nature of so many more RF devices these days?
Well, obviously frequencies are going up across the board. I mean, we're starting to talk about frequencies now that even 5 or 6 years ago would be considered ludicrous, but they exist now, and everything. My major experience level is at much lower frequencies, but everything that occurs down there occurs the same at high frequencies, with some added things that happen, like current. The forward and return path. The return path tends to congregate directly under the forward path in traces. Yep. So at low frequencies, if you have a nice wide ground plane, then everything's fine, because the current will kind of go through the whole plane. But at high as you go up in frequency, it's the path of least inductance in that case, and so it tries to minimize the loop by concentrating the current directly under the forward path, which is an added detail that you don't have to concern yourself so much with at lower frequencies. So the basic concepts stay the same, but some of the details change a little bit as you go up in frequency.
So when you say at lower frequencies versus higher frequencies, what frequencies are you talking about? Megahertz, gigahertz?
Basically, when we start talking about low frequency versus high frequency, generally it's someplace between 10 and 100 meg.
Okay. It's
a dividing line. It's not truly defined, but generally below a megahertz is a little bit more simple than the higher frequency stuff. And once you start getting above 100 megahertz, then you have to start looking at all these things a little bit differently.
So basically the same frequency threshold roughly that at which you need to start worrying about your circuit radiating.
Exactly.
Yeah, I always think about that stuff whenever I see a trace jumping over a ground plane. I always think about that, like the return path coming back underneath, and then it hitting that ground plane just like a cliff, and it just going, no, I'm going wherever I want at this point, and then your EMI testing fails immediately.
Yeah, exactly, and we've covered that in some of our stuff in the books that have to do with, if you are routing a trace and you have a discontinuity for whatever reason where traces are crossing each other or whatever, that all of a sudden the electrons that are running around that return path all of a sudden go, ah, because the place they wanted to go is no longer available for them.
Yeah. Yeah, they go Evel Knievel over the gap, and they just jump off into space.
Yeah, and that's what happens when when you put things like that on a board, as they do, they radiate out, and that causes all sorts of problems. When I was back doing most of my design work, the radiated field testing still wasn't done all the time, and there weren't as many commercial rules about what you could do. But that's one of the other things that's happened as the whole commercial and consumer stuff has gone up into these high frequencies. With cell phones and wireless and Bluetooth and all the rest of that stuff, that you've got so much stuff floating around in the air that you are worried now about how much stuff that you're sending out and how much you're actually being able to receive, all this anonymous stuff that's floating around, and how much that affects you. Both of those have become a lot more rigorous concerns than they were, several years ago.
Yeah, your cube mate's got a hack RF in his cube, and he's just spewing out some kind of SDR frequencies, right, Mike? Am I right?
Something like that. Yeah.
So do you ever? So Hank, do you? Because I know Analog Devices has a bunch of up converters, down converters, and mixers and all that stuff. Did you ever jump into that side of things, or was it mostly more on the low level analog stuff?
I touch it occasionally, but my comfort zone is definitely down at the slightly lower frequencies.
Yeah.
But I've heard enough war stories and can relate it that I can help people out a little bit, but it's really not really where I have my strength. It's really at the lower end of the spectrum, where things are a little sane.
Yeah, one thing I really like about the RF chapter of your book is your section on mixers, and you have a diagram in there that just shows like a sine wave RF and a square wave LO, and then the product. Mm-hmm. And it is amazing how hard it is to find a diagram like that. It explains how mixing works so clearly, and it took me a long time when I was getting into RF to really grasp just exactly what that diagram expresses.
I won't take credit entirely for that. A lot of what's in that book has been gleaned from there's a lot of smart people at Analog, and a lot of that stuff has been things that I've seen that other people have done. But that particular diagram, I remember it. It was something that made a lot of sense to me when I first saw it, and that's one of the reasons why I wanted to include it.
What about the chapter on sensors and stuff like that? So I'm always interested to learn how things hold up over time. I mean, have you found that a lot of the sensor stuff has held up, especially as we've kind of moved into more integrated sensors these days? It's
basically the same thing. At Analog, we still do a lot of business in the industrial marketplace, people are still measuring temperature. People are still measuring pressures, and they're using that to control systems. That hasn't changed. I mean, the way we interconnect things has changed. Our ability to measure those things has changed in that we can now do it at much higher accuracies and at much smaller dimensions than what we were able to do before. But the basic need to be able to measure things and control systems based on those measurements, that hasn't changed, and it's not likely to for a long time. So there's still a lot of that kind of stuff around.
We were marveling at the that new ADUCM 350 last week, and I've looked at the 360 before as well. And those, I mean, the amount of integration these days with like onboard, that thing's got a Cortex M3 in there, and it's like this whole analog front end and power and all this other junk. It's just like, I mean, it's getting to the point where, I mean, these sensor chips are starting to approach, because they have micros in them. They're pushing 1,000-page manuals now too. It's insane to me. So it's cool, but it's frightening as well.
Well, there's the whole integration thing is a two-edged sword.
Mm-hmm.
I mean, it makes a lot of sense that if you have a target market that can support development of highly integrated sensors, then the fact that you're putting all that stuff and taking it up off a PC board and putting it on the chip itself makes a lot of sense. The problem is trying to make that fit for target markets that aren't, I said that wrong. Trying to make that fit for markets that aren't the target market, and trying to bend them around to do other things. That's where it becomes a little shaky sometimes. But if we could integrate everything, we save a lot by having all this stuff in close proximity, so we don't have the same kind of radiation issues. It's the kind of thing where we only have to solve the problem once. And once we have it solved in the chip, then that every time that chip is used in a different application, they don't have to worry about all that kind of stuff again. So, and with the reduction in size of the geometries that they use to build integrated circuits now, you can shove a lot of stuff in even the very small packages.
Yeah. Oh, yeah. Yeah, I think that one we were talking about is like a 8x8 BGA or something like that. It's
and
insane.
the problem with that is it could be even smaller if they could get the ins and outs. The problem is getting in and out of the chip. That's if you were to take a look at what the active circuit area is compared to the size of the package, it's pretty small. It's again the number of trying to get the things in and out that becomes the big issue.
That seems to be true for a lot of parts, and as we go into higher and higher frequencies, that becomes a bigger problem, having to have a big package for a small part. Do you see any technological advance on the horizon that might alleviate that problem?
Well, I mean, we've gotten to the point now that some of the packages are basically the size of the die. There's some of those things that in the smaller packages, the smaller functions where you don't have as many pins.
Right.
We have what we call the bump die packages, which are, basically the size of the die itself. I don't know how much smaller you can go with that. The larger functionality where we have, the higher integration, the ins and outs, basically, if we could find a way to cut those down, we could make smaller packages. But that's why the integration at the higher frequencies may not happen quite as fast, because of the fact that there's these technological hurdles we have to cross, having to do with getting signals in and out.
So I'm curious about your audio hobby. Can you tell us what some of the projects are you've done?
I'm a musician, so a lot of my stuff has to do with audio. I actually wrote an article, late 90s, mid to late 90s, I guess it was, about making an outboard DAC for a stereo system, where you take the AES EBU input, and then convert that into a DAC that was done outside of the chassis, so that I optimized power supplies, and I went to the ludicrous fringe on the filtering on the output, and it came out pretty well. I actually had some good reviews from the stereo Golden Ears crowd. So that's still playing in my system at home.
What is the ludicrous fringe? I don't know that term. I'm sorry.
Excess is not nearly enough. It's my reconstruction filter on that thing was 7-pole.
Oh my gosh!
At the time, most people were operating with maybe 4.
Uh-huh.
3 was a lot more typical. And then,
so that was a Spaceballs reference then, or what?
Hey, why not? The name of my first CD was Unknown Artist, Unknown Album.
So,
like
what kind of music do you do? What instruments do you play? Or
keyboards and guitar mainly. A lot of I do a little bit of electronic stuff where I use these virtual plugins to make my keyboard sound like other things.
Yeah.
A cello, harmonica, harpsichord, whatever. I said, because of my chronology, my basis is in the folk rock, late 60s type of thing. That's where I started playing. And so there's a little bit of that. It's pretty eclectic. I mean, I go across a lot of different things and to kind of give them my own little treatment.
Yeah, we were talking a little bit before the show about the commonality amongst a lot of engineers. I don't know, Mike, if you've ever played music. I used to play a lot of music, and just how it seems to be a common thread a lot. I'm not sure. We're not sure why. Hank said it's possibly because of the math. I said it's to try and meet girls. I mean, I think we're probably both right.
Gotta do something.
Yeah. But that's really cool. That I mean, if you start passing the test with the audio files on the actual DACs, that's
it was one of those strange things where it measured well and it sounded good. So it's best of both worlds.
That's a rare combination.
Yeah.
So we had a couple questions from someone over on Reddit where we collected some questions for you, and I thought we should get to some of those. We usually kind of skimp on the asking questions from people, but there's good ones here. First one was ADI app notes. I mean, obviously we talked about yours, the Staying Well Grounded and the book. Are there any others that you find yourself going back to that people should know about and should go out and find and memorize and read and that kind of thing?
Oh, there's a ton of stuff out there, and there's good stuff from a lot of different sources as well. So, kind of poke around and see what you can find. In terms of analog, probably the precursor to my Staying Well Grounded was something that was called, it was written by Paul Brokaw back in the late 60s that talked about grounding and making things go right. That's still highly applicable. One of the things that we run into lately is at Analog we have MEMS functions, accelerometers and gyroscopes and the like, and not a lot of people are really familiar with the mechanical to electrical conversion process. We all know about volts and things like that, and we can understand amplifiers where you put a little bit of voltage here and you get maybe a little bit more voltage out here. But when you start talking about measuring gravity and tilt and those types of things and converting that into an electrical number, that's kind of confusing at
yes,
first until you've spent some time doing it. And it basically comes from experience. So anything that has to do with the MEMS, I think, is highly useful if you're going to go into that area at all.
And you think that's still necessary even, I mean, like, because there's such high integration with these things these days too, especially, it feels like a lot of these MEMS, these 3-axis, 6-axis things, they just crank out coordinates these days. But you still think it's necessary to understand a lot of that underlying stuff?
Well, I think it helps to have a basic understanding of how the things are working. It basically, I mean, we still field a lot of questions that have to do with, somebody doesn't really fully understand the relationship. For instance, on the accelerometers, it's a CMOS sensor. It's working with zeptofarads. I mean, it's just way down there, and that small amount of capacitive change then is converted to a voltage, and so you've always got the problem of Gaussian white noise type things, and how that electrical noise and how that kind of affects your accuracy in your mechanical motion is, something where you've really got to kind of think about it a while to get comfortable with the correlation there. So, there's those ones. The other one that we have, not so much anymore because people are getting a lot more used to it, but for a long time, the whole thing about how sigma delta worked.
Oh yeah.
Confused a lot of people. And so there was a lot of stuff in there about, read it a couple of times because the first time you go through it, you're going to say, nah, I don't think so.
That's witchcraft.
But it really does work, and it takes a little while for your mind to really get around it and say, oh, well, maybe it really does do like that.
I get freaked out sometimes when I'm looking for parts. I'm looking for converters, and I'll, do a price per sample rate comparison and get totally thrown off because some parts are sigma delta and some parts aren't. And
yeah. Oh yeah. You're like, oh, I need 20 bits, right? And find a star converter, and it's like what, $35 or more.
Okay, now you've said the magic word. The duck's going to drop down here, and you're going to get your reward. But resolution and accuracy.
Yeah.
These are not the same thing.
No, they are not.
Resolution is the number of bits that wiggle, and accuracy is the number of those bits that actually mean something.
Right.
So, for instance, our sigma delta converters are 24-bit data words, so they're 24-bit converters. But you got to take a look at the SNR to see what they really are in terms of, because people are expecting, to look at the 24, they're going to ground the inputs, they're going to look at the 24 bits, and they're expecting nothing to move.
Right.
Then no.
No. sorry, folks. Physics and stuff. Do you use the term ENOB or no? Is that not a kosher term around analog?
Well, there's a couple different things that you have to look at from a couple different points of view to sort everything out. So, equivalent number of bits is one way to look at it. I tend to more look at it as SNR, signal to noise ratio, but they're really the same thing. There's a really strong mathematical correlation between the two. 6.02 times the number of bits minus 1.76. So that it's really two different ways of looking at the same thing. To me, SNR, because I came from a strict analog rather than a converter type background, but if you're mainly working with converters, ENOBs may be more in your backyard than SNR is, in dB. So
yeah, right.
Being able to think about them in both terms is probably a plus. The same thing when you're talking about converters, same thing talking about the frequency domain and the time domain. To really, really understand converters, you have to be able to go back and forth between the two pretty easily, because there's some things you understand in the frequency domain and there's some things you understand in the time domain.
Could you give us an example of that? What do you mean by that?
Okay. Let me think about this a second. aliasing.
Okay.
Okay, so aliasing is when different frequencies appear to be the same once they're converted. It has to do with the frequency of interest versus the sampling rate, and read my book.
Not many people get to say that, folks.
So, and that's something that you can look at both in the frequency domain, because you can start seeing how when you slide the analog frequency up relative to the sampling rate, how the aliases then move in the opposite direction.
Right, yep.
And another way to look at that is just take a look at, which I've put in a couple of the things we've done, is that you take 3 different sine waves at 3 different frequencies, and you sample them all at the same. The lower frequency, 10 samples, converts to 1 cycle of the input. In the middle one, 11 cycles will fit in those same 10 slots, and in the top one, 21 cycles fit in the same slot. Just look at the instantaneous conversion of each one of those 10 time things, and they're all the same. And so that's another way of looking at, in the time domain, what you're seeing that can also be expressed in the frequency domain.
Yeah, that's
I'm always a stickler for trying to get people to plot their time domain digital signals as distinct points instead of connecting the dots with lines. Because then, you start connecting the dots and you fool yourself into thinking that there's something there that isn't.
Yeah, and you got to remember how a converter works. It takes a series of discrete samples, and it really doesn't know what came before, what comes after.
Mm-hmm.
It doesn't know about the transition from one sample to the next. All it knows is that its clock is coming through and says, take a sample now, take a sample now, take a sample now.
Yeah.
It does that. It spits back the answer, but you don't really know what happened to the signal between those 2 samples, and it could be one of several different paths it could have taken to get from one point to the next.
Yeah, that's a really good point.
So, I mean, that's one of the things where just give you an idea of how you got to kind of go back and forth between the 2.
Another question we had on Reddit was similar to what we were talking about before. As chip integration increases, where do you see PCB design going in terms of changes that need to happen, and how like listeners and other engineers out there would need to start accounting for that kind of thing?
Going back to as things are getting faster and faster and smaller, PCB layout is an issue because, again, how you partition the board, how you lay things out, how you have signals connecting from one part to the next part can all affect how the thing works. And if you're not wise about how you partition the board, then things will tend to get kind of spread out from an electrical standpoint, more convenient, but from a physical standpoint, less convenient. Like you minimize this trace, but to minimize that one trace, you've now made other ones more complicated. So, and as the clock speeds go up, then the possibility of radiated interference goes up. And so you need to start talking about keeping those kinds of things under control. Also, signals, even digital signals, are becoming more and more analog. We're starting to talk about characteristic impedances of traces connecting different points. Even though we're talking about strictly digital signals, now we're talking about having to match the impedance in and out of these parts. We start talking about the trace lengths having to be matched within a certain wavelength of especially when another thing we've done recently is gone to a lot of differential signaling. Mm-hmm. And so when you talk differential, those two paths that are the two phases of the signal, you got to be pretty well matched, or you're going to start running into problems as well. Also, the reflected. So if you're not, if your traces aren't matched, you're going to have some signal trying to reflect on the trace as well. And those are all things that are non-schematic components. It's
yeah.
You don't see it as a resistor or anything like that on the schematic, but it is a real component that's on there, and you have to kind of keep an eye on that.
Do you find yourself using more of like the signal integrity tools, like for doing trace like matching and stuff like that? For I forget what that's called, that simulation method. Is it IBIS models and that kind of thing?
IBIS models, yeah.
Yeah, do you do that a lot?
I haven't done so much with that, to be perfectly honest. Actually, another war story. That's how I met my wife. She's a printed circuit board designer.
Nice.
Oh yeah.
Match made in heaven?
Not all the time.
Well, no, right. Not when board layout's happening, right? I mean,
no, because
you can argue about where the signal goes and everything.
Yeah, she was not from an engineering background, but more of an art background, and that actually gave her a leg up on doing a lot of these things, because when she was looking at the schematic, if you have a well-drawn schematic, it kind of makes it easier to kind of group things into the right areas. Excuse me. And, so she may not have had all the electrical background to understand all these things, but, from an art standpoint, if it looked right, it probably was better that way. And in most cases, so I worked with her a lot in trying to optimize how things were laid out. And this was right at the beginning of the CAD period, when at that time, I would say that the automatic routing programs were a complete waste of time.
Yeah, I think they still are, personally.
I think that they probably are better than what they were, but I think that there's still a little bit that the human eye can kind of do in things. And a lot of it has to do with how they prioritize. A net list will just prioritize whichever's next on the list,
Yeah, right.
And that may not be the optimum. You may want to optimize some other trace, and so it's something that, in my mind, we really haven't been able to develop an expert system yet in the computers to do a really good job of that.
I think if you don't have time to do the layout up front and you're not willing to put the time in, that means you have a lot of time later on to be debugging and wanting to pull your hair out.
Yeah, and not only that, even if you know what you're doing, you're not guaranteed success every time on the first time. Another story from analog. We were making a cross-point switch, analog cross-point switch for video. 8x8 matrix. So 8 inputs can be routed to any one of 8 outputs.
I think I've looked at that part.
The evaluation board, even though we kind of know what we're doing in terms of board layout, we had to go through several revisions on the layout of the evaluation board to get the crosstalk on the board lower than the crosstalk on the part. Obviously, an evaluation board that kind of ruins the performance of a chip is probably not the way you want to go.
Look how great our part is, folks. We promise it's better when you do it.
So that's the kind of thing where I'm talking about that even though you do this, and I tell the customers this all the time, it says, expect to go through at least one revision of your PC board. Just put that into the schedule while you're making the schedule, because I don't care what evaluation tools you use, the chances of you doing everything right the first time are slim. Now, as you gain experience and you've made enough mistakes, and you hopefully learn from those mistakes and decide not to do those non-optimum tasks the same way, your percentages improve. But there's so many things to look out for, in terms of parasitics with how traces talk to each other in ground planes and the like. It's really, really hard to keep all of that stuff in front of you all the time, especially since the way things are today, that none of us have the amount of time that we'd like to have to do any kind of project.
Right. You can't really stress over it too long and overthink it too much because it has to get out the door and you have to get on to the next thing.
Right.
And if the next thing is debugging 2 designs ago, well, that's just what it is, right?
Yeah. And there's a fine line there, and you have to do a little bit of it, or to your point earlier, if you don't take the time at the beginning, what was the old automobile thing? Pay me now or pay me later type of thing.
Exactly.
And that's true in this respect as well.
Do you ever do you ever get sick of analog? Do you ever like, one of these days, I just wish I would have been a code jockey, or I don't know any other derogatory terms for software people.
With the exception of trying to find an industry that wasn't as strongly male dominated. I don't think so. I mean, it's challenging. It's interesting. I learn all kinds of new things. I'm looking at all sorts of different projects, different ideas that people have. I find all of it, well, most of it, pretty interesting.
Yeah.
So I think that there's a lot worse things I could have done.
I'm with you, man. I mean, I'm I'm on the same path. So, what about like other people that are kind of like coming out of school now, or thinking about going into college for like analog? Any advice for them? Anything like that?
Well, what we've been able to see from analog devices since is that most of the people that come out of school are very well grounded in digital stuff. They can write code. They can program FPGAs, and they've got a real good feel for that. But the analog stuff, it's still the black magic, and you still have the Merlins running around who understand it, while most of us don't. And I think that if somebody was really interested in kind of adopting that as their major area of study, I think that it's something that not maybe offered so much, but it's really kind of an interesting. I mean, there's so much you can do and so much you can. I mean, we're still talking about stuff I was doing 20 years ago, and how many digital guys are talking about what they did with a 6502,
Yeah, the C64 guys are, right? That's
Yeah.
about it.
So how do you recruit good analog people? I mean, you obviously need a lot of analog IC designers at Analog Devices, but you also need system level people like yourself. I mean, where do you find them?
Quite often we take people from the industry quite often. So, we've had applications people who have come out of the other side of the fence, if you will. The other thing is that it's kind of a guru mentality that you have the people who have the basic skills, and you sit and let them learn from the people who have more practical experience in these particular areas.
Yeah,
because I mean, I know from my own personal that what I learned in school just taught me how to learn when I got out in the industry, and the real practical stuff was all stuff that I learned after I got my degree.
I think it's going to be interesting too because we've been talking about a lot of the increasing integration, right? And so my argument against people coming in and showing me these new parts and stuff is always like, you're taking away the fun stuff, right? And that's always my argument for showing me these new chips. But at the same time, they're also very useful. But what I wonder is moving forwards, like if there'll be like a false sense of security, like, oh, well, I can just talk to the registers that are in an analog front end chip like that ADUCM 350. And not have to worry about the analog stuff, but then there'll also be this kind of like this latent background. Well, yeah, but you you stuck it to a piece of bubble gum. You didn't actually put it on a PCB, right? I mean, like that, like you still need this baseline knowledge in order to actually use a lot of these integrated chips. And I wonder how that's going to affect things going forwards.
I don't think you're going to lose that completely, because the chip you were talking about. I mean, you've got all these analog front end things, but you got to connect them to something, right? Or it doesn't do any good.
Yeah.
And
right.
so there's always, I don't think we're going to get to the point where we're just going to have a piece of silicon that does everything every time for everybody everywhere.
Okay.
The world's varied enough that's really not what we're going to get. And we're still going to have people understand that I've got this really nice chip that does a whole ton of stuff.
Yeah.
But I still got to connect it to something to make it work and make it useful, right?
Yeah, I guess on both ends, right? Analog and digital.
Yeah, in and out both, right.
Yeah. What is, I mean, you're on the inside. I know you can't tell us about like the super new stuff, but what about, what are some trends or some technologies that you've seen that are really exciting to you on the analog side of things?
Well, the vast majority of that is more evolutionary than revolutionary. It's going faster and all the rest of it with, smaller and faster and all those things that people want to see nowadays. It's rare that something completely new comes out of the woodwork. It does happen. The MEMS stuff is a prime example. Before that existed, there was really no way to do that kind of stuff. And then all of a sudden, we now have a whole line of accelerometers and gyroscopes and the like, and people can do some interesting things that they weren't able to do before. We have isolators, that go across barriers, and, that's been done for a while, but, we came up with a new way of doing it that was a lot more cost effective, lower power. Basically what we did is we went to transformers instead of capacitors or optical to do the conversion. So that was a new technology that we came up with. But a lot of the stuff is, again, just taking what we have and making it better, smaller, cheaper, faster, those types
more
of
accessible,
things.
right?
Yeah.
Yeah. Yeah, because that the isolator is a great example. I mean, people used to actually do that with transformers, right? I mean, they would have, drivers on either side, driver, receiver, push a signal across the transformer, and just sat there doing that all day.
Yeah,
now it's a little tiny one.
Yeah, and our value added on that was coming up with transformers that were so small they could be, multiple channels could be put into a normal size IC.
Mm-hmm. Yep.
And there were some practical issues. Well, what about sensitivity to fields and the like? And it turns out that those guys are actually pretty good because they're so small that the enclosed loop doesn't couple a great deal of energy in there. And if you take the outboard transformers, then you've got the traces going to the transformers. You've got the transformers sitting there, not quite as small, so they are more susceptible to fields.
I'm always amazed too. So I always wondered about how those things actually worked. It took me a long time to realize that it's actually always sending pulses, and then like for a low, I think this is how it works at least. It's always sending a single pulse for a low, but then when a digital signal goes high on the isolated side, it's actually sending a double pulse, and that's how it can tell that transition basically, or something like that, right?
Yeah, it's they put a pulse through at every transition. So it doesn't really understand low and highs. What it does is they know that the input switched from one to the other, and so it goes across. And the reason that that's required is transformers are notoriously bad at passing DC.
Right.
So, if you have a signal that's not changing very often, it basically looks like a DC signal. And so by just putting the pulses through on the transitions, then that allows the signal on the isolated side to transition from one state to the other, and it'll stay there until it gets the next signal coming through saying, okay, flip it back the other way. Yeah,
and for a long time, for me at least, it was, I didn't quite understand the draw of the whole, isolator thing. Like, why are people even doing it? And then I went into the industrial market, and it's like, you better be doing it because, and even just in a more practical manner too, you have common mode voltages that might be anywhere all over the map. You might have, 1,000 feet of wiring where that thing's sitting 100 volts above where you're sitting, and then you could have some serious current flow and actually hurt yourself at that point or hurt your devices.
Well, to the point we were saying earlier, just because these 2 points are grounded doesn't mean they're the same potential.
Mm-hmm. Right.
In a big industrial installation, it's the same thing. The details are considerably different. The distances are better, are longer. The potentials you can have between them can be much larger. It turns out to be mainly a safety issue. I mean, one of the primary uses of isolator technology is in the medical field. If you have a bunch of things connected to a patient, you really don't want to make him your star point.
That is an excellent point.
He'll become some lawyer's star witness.
So, there's a lot of reasons why those kinds of things. Now, and then there's some reasons that may not be too obvious. One thing that I used the isolators for is I made a A to D converter, again, audio application. Mm-hmm. And I wanted this is probably seriously over-designed, but, I know where to get
That's
the parts
most fun,
cheap.
Though. Come on.
Yeah. I know where to get the parts cheap. So it's, I actually had my converters running, and then it went into one of these isolators, and then all the stuff that happened on the far side there was absolutely no chance of having return currents flow.
Yeah. Yeah, I thought about that because I have this cheapo Behringer, ADC effectively, and a DAC on board, and it's USB based. But then you can literally hear, the power supply noise from my computer coupling through to the actual analog output, and it's like, it's terrible.
We have a solution for that too. We have an isolator that's designed specifically for USB. Yep. And again, this may be slightly overkill, but I actually took one of those and put it in my USB line to my outboard A to D, D to A on my main music capture system, because the A to D, D to A was actually powered off the USB line, and that's a really ugly signal coming out of the computer.
Yep.
So I found it advantageous to break that connection, have an isolated side, and then put a super clean 5-volt to power the peripheral out there, and not have that communications back and forth. And you can, under the right circumstances, hear the power supply. If you crank everything up and listen really closely, you can hear that kind of stuff going on.
Yeah, it's crazy. Well, that's another cool thing too about some of those parts. The isolator parts starting to have power supplies built in too. I would like that too, because then you don't even have to worry about that anymore. It's not going to be a clean power supply. It's still, some DC to DC isolated switch mode, but that's just
cool.
We're
talking about small amounts of current. The DCs and DCs can be made relatively clean because again, you're not spiking a lot of current, so the interference levels are reduced.
Yep. So any other technology coming down the pipeline that we should keep an eye out for?
Again, just going faster. I mean, we're talking about in our phased lock loop group. We're talking about going up in frequencies, 17 gigahertz and above, and I'm sure that they're looking at things that are even faster than that.
I like the sound of that.
Yeah, I have a hard time just getting my head around 17 gigahertz to start with, but that's where everybody's moving up to. That's where there's the migration is going that direction. So if that's where people are going, that's where the people who's like Analog that are supplying the parts to make the next generation thing have to be looking at that, and then the next step beyond that as well.
Yeah.
So again, it has more to do with evolution than revolution.
Yeah. Well, Mike, what about you? You got any other questions for Hank?
I think I'm cleaned out.
Yeah. This has been this is like a short course in analog design. That's exactly what I hope for and more. It's
Absolutely.
So Hank, how are we going to find out when you actually are on the road so we can, bum rush you with Amp Hour listeners that want to ask you questions and hear your seminars?
Well, I'll tell you what. Next time we have a seminar thing coming up, I'll send you through the Amp Hour thing a notification, and you can put it on the notes to people all over the place. And we welcome everybody to show up.
Terrific.
That's awesome. First come, first serve, folks. And you know what? I'm hearing about it first from Hank, so I'm number one.
Yeah, Hank, like I said earlier, it's unfortunate I don't get to do that nearly as much as I used to, but, it does still happen.
Yeah. Well, if there's anyone we can talk to try and get you out on the road more, let us know, and we'll be annoying wherever we need to be in order to get you out on the road.
Okay, well, we'll take that offline because I don't want to put any kind of names out here right now because it may not be appreciated,
And here's the CEO's cell phone number. And okay, great. Well, Hank, thank you so much for being on the show. I really appreciate it. Where can people find your future writings as well? I mean, is it mostly on the analog site?
Mostly on the analog site. I'm actually completing a couple of more articles in a series that I've been doing on phase responsive filters that will be on Analog Dialogue, whatever turnaround time is to get into there. I'll probably have the final drafts into them within the next 2 to 3 weeks. And then whatever, however long it takes to get everything laid out, drawn up, and scheduled into their system.
Yeah. And that's a great reference as well. If people don't know, that's the newsletter that Analog Devices sends out, and it's very, very valuable. So,
anybody who doesn't know about that should look into it. And there's a lot of good information in there.
Definitely,
they're all archived, so you can actually go back and take a look at stuff that's been there before. It's not completely devoid of marketing, but it tends to be much more technical. And there's a lot of good articles in there. Even I've learned stuff out of there. So, it's like a shark has to keep swimming or he drowns. You got to keep looking at this stuff all the time, or you just become out of date.
Yep, got to keep building outboard DACs that 7-pole filters on them. That's how you keep sharp, people.
Hey, why not?
Yeah, it's awesome.
Nothing succeeds like excess,
Exactly. I like it. Well, Hank, thanks again, and Mike, thanks for jumping in for Dave as well.
Yeah, thanks for having me. It was great to talk to you, Hank.
Yeah, this was good. I hope some people found some useful stuff in it, and if anybody needs to get a hold of me, it's hank.zumbahlen@analog.com. I welcome people to send me stuff. I may regret having said that, but
they'll be. I'm sure they'll be respectful. They always have been in the past. So
yeah. So if there's some I can do to help people out on individual things, that's what I do nowadays. So have at it.
Awesome. All right. Thanks again, Hank. We'll talk to you soon.
Okay. Thanks a lot.